could you give me screen sharing
Yeah.
power? Thanks.
Yeah, please share the slides. And in the meantime, let me just invite everybody to the today's IRC seminar. We will be hearing about indirect and direct terrestrial and extraterrestrial searches for dark matter. It's certainly one of the most exciting areas in high energy phenomenology. So over to you, Nirmal. Let's hear from you.
Thank you very much, Ayan. Thanks everybody for being here. It's always exciting to come back and give a talk at ITM, although I'm not really there, but always warms my heart to address this audience. So let me get straight into it. But before I go to my talk, I want to explain what I mean by this title. So when we didn't know what an atom was made of, Ernest Rutherford tried to understand it by throwing things at it and looking for the scattering products. And today we don't know what dark matter is made of, but what we do know is that it is being thrown at us well understood particles. So in principle, we should be able to set up some sort of a Rutherford experiment, except in reverse, because now the beam is the unknown and the target is the known entity here. So that is what I'm going to be talking about. And in particular, I'll be talking about a couple of reverse Rutherford experiments, as I call them, that I have proposed and I'm actively involved in. Okay, to begin with, dark matter is this substance that does not emit, absorb, or reflect light, is seen all over the universe at all distance scales, makes up most of the matter of the universe, and stubbornly refuses to tell us what it is made of at the microscopic level, despite extensive interrogation. We do know it's there because it pulls on everything else that we could see via the force of gravity. To illustrate this with a two-body example, the presence of an unknown object could be inferred by measuring the distances and the speeds of the object that a heavier object is pulling on, right? So this is how we discovered black holes, and indeed this is how we have weighed the sun. Now, the acknowledged pioneer of the field of dark matter is the Swiss astronomer Fritz Zwicky, who in 1933 looked up at the Coma cluster and wanted to measure its mass. And what he did was convert the light that he saw to mass and use the virial theorem and found that the galaxies in the Coma cluster were just traveling too fast. And this led him to propose the existence of an invisible missing matter that he called dark matter, which he said must be present in much greater amount than luminous matter. Now, that didn't lead scientists to take this question seriously until the 1970s, when Vera Rubin and Kent Ford, using the latest sophisticated spectroscopy that they had developed, measured precisely the radial speeds of the radial and azimuthal speeds of stars in the Andromeda galaxy and several other galaxies, and found that these galaxies were basically spinning too fast, especially out to very large radii where there is supposed to be very less matter. So that more or less established the presence of dark matter in the universe. Even then, there was no real sense of crisis, because even until the 1980s, if you were to ask an astronomer what dark matter is made of, they would just point to this, the periodic table. It was all stuff that was too faint to see. Or it was all probably planets and white dwarfs and brown dwarfs and red dwarfs and neutron stars and black holes and so on, collectively known as massive compact halo objects, right? Except when we move on to the 1990s, when people try to look for these planets and white dwarfs and brown dwarfs and neutron stars and black holes, they just didn't find them in gravitational microlensing surveys. And to make things worse or better, we got very good at cosmology, basically precision cosmology. And now we were able to very precisely tell how much ordinary matter there was. By ordinary, I mean the visible matter or baryonic matter that makes up planets and stars and so on. So how much of this matter there was in the early universe in the proportions of elements cooked in the Big Bang, known as Big Bang nucleosynthesis, and in the relic radiation left behind by the Big Bang, known as the cosmic microwave background, especially in its temperature fluctuations and using the power spectrum and so on. The grand conclusion of these cosmological measurements was that ordinary matter made up around only 15% of all the mass that you see in the universe, and that this unseen dark matter makes up as much as 85% of the matter in the universe. And that's when the crisis set in for fundamental physics. In the meanwhile, we have been amassing a lot more evidence for dark matter. For example, simulations of the large-scale structure of the universe, which match with observations, tell us that this structure of the cosmic web with all these filaments and nodes and so on could not have been formed without some form of invisible cold matter. There's also one of my favorite evidences for dark matter, known as the bullet cluster, sometimes touted as the in-your-face evidence for dark matter. This is basically a structure composed of two clusters, one which has sped through the other. And if you look at it, you can look at it in two different ways. And what you find is that this bullet cluster, this combination of two clusters, shines in X-rays in regions where the mass is not concentrated. Basically, the mass is concentrated far away from these clusters, which you infer from gravitational strong lensing. And that tells you that some invisible mass has moved much farther apart, while the visible gas has been slowing down due to electromagnetic friction. So there you have it. There's so much astronomical evidence that we have collected for the existence of dark matter. There's almost no doubt these days. I mean, there is no doubt these days that dark matter actually exists in the universe. But all this evidence is gravitational in nature. But if you really want to know what it is made of at a microscopic level, we need to know its particle physics fingerprints. All right. And one of the best ways to probe the particle physics nature of an entity is to set up a scattering experiment. Now, the historic virtues of scattering cannot be overstated. Scattering of the atom with alpha particles is exactly how Rutherford, as I was mentioning, discovered the atomic nucleus in the center of an atom. Scattering of X-rays and studying diffraction patterns is how Rosalind Franklin and her team discovered the double helical structure of the DNA. Scattering of nucleons in the deep inelastic regime using electrons was how SLAC and other experiments discovered the existence of quarks and gluons and so on. Right? So scattering really is one of the most important tools in the tool shed of a physicist looking for the fundamental nature of an entity. So naturally, we would like to set up a scattering experiment for dark matter as well, where the goal of the experiment is simply to determine the scattering cross-section for dark matter scattering on nucleons or electrons or something. Because the scattering cross-section is an intrinsic quantity that does not depend on how you set up the experiment. And knowing this intrinsic quantity could help us pinpoint the theory of dark matter. And the strategy here, as I said, is what I call the reverse Rutherford scattering experiment, where the beam is made of dark matter particles that are surrounding the Earth or the solar system, which makes up the unknown species here. And you let the dark matter strike nuclei or electrons, basically well understood species, as your target material. And then you study the changes in targets, such as how much energy and momentum was transferred in the scattering process. And the inputs to this experiment are nothing but the average speed at which dark matter moves in the solar vicinity and the density of dark matter in the solar neighborhood. And thankfully, we do have a very good notion of what these quantities are, as inferred from stellar motion in this part of the Milky Way. And what we know is that dark matter in this area, in these regions, moves at 1,000th the speed of light. So it is non-relativistic. And the ambient density of dark matter is about 0.3 GeV per centimeter cubed, which comes to about 2 protons per teaspoon.
So I have a
Nirmal,
question.
Yes, please.
Sorry, Ayan.
please.
So you're assuming a WIMP-like dark matter in this, right? Or are you also thinking about ALPS or things like this as well?
Up till this point, I have assumed nothing. Everything here is from astronomy. ALPS or primordial black holes or WIMP dark matter or anything, we do know just from the measurements of stellar motion in the transverse direction near the solar neighborhood, that it has dark matter should move at 300 kilometers per second by also looking at rotation curves of the galaxies, of our galaxy. And we also know the density from this. So so far,
the
no
relic density is just the only thing assumed here, really.
Exactly. And exactly. And I wouldn't even call it the relic density. It's just, these are just the inputs, experimental inputs to dark matter. I have not even gone to theory yet.
Okay, observational inputs, fine.
Observational,
fine.
Exactly.
Understood, thank you.
Yeah, great. That's a great question. Any other questions up to this point?
Yeah, I have something similar. So to have the scattering, you must also postulate some kind of force between the dark matter and the, so is it gravity or gravity combined with something else?
So just gravitational scattering, that since we've already observed that, that's not really telling us what the microscopic identity is. And what I mean by we've really observed that is all the evidence that we have amassed for dark matter comes from gravity. And since it's a weak force, since it's a really weak force, we don't really know what the particle physics identity is. What we are hoping for is that the force would be stronger than gravity. Maybe through a fifth force, or maybe through one of the fundamental forces that we already know, or maybe through some mixing with the Higgs and so on.
So basically, this is WIMP-like scenario. Or
something like a WIMP, and I'll come.
Particle. That,
exactly.
Okay, you're coming to that. Yeah.
At the least, and I'm assuming this is a particle so far. Yes.
Yeah, and then the other question is that there are also some direct Rutherford type behavior, scattering also possible, right? Suppose there are people who are investigating like very high energy dark matter going through a neutron star, for example. And,
oh dear, that's exactly what my talk is about.
Oh, okay, very good. I say.
Yes,
okay,
sorry.
Okay,
yes,
sorry.
That's exactly what the talk is about. Yes, yes, but yes, yes. And one of the people who proposed that was me. the neutron star idea.
Great to know. Great to know. Okay.
Okay, so I think where I was we in principle we should be able to set up a reverse Rutherford experiment with these inputs. And as a matter of fact, experiments like these are being conducted, have been performed. They're continuously being performed for the last 4 decades or so, going under the rubric of dark matter direct detection. And here are some latest results from such experiments in the plane of the cross section for dark matter to scatter with nucleons versus the dark matter mass, because these are both unknowns. So to interpret, so the plots that are being shown here are various constraints or basically upper bounds on the cross section as a function of mass, coming from the various experiments that are labeled here. And what we've learned is that just interpreting this with a broad brush, we do know that at least dark matter at around 100 GeV, which is the electroweak scale, does not interact with nucleons with a cross section that is greater than 10 power minus 46 centimeters squared, which is a ridiculously small cross section, which is testament to how good these experiments have become, right? Now, to put this plot in context, let me zoom out and show a bird's eye view of the exact plot that I showed in the previous slide, except now the cross sections are spanning about 40 orders of magnitude, and the masses are spanning about 20 orders of magnitude. Okay, so this range of masses is where you expect the dark matter to behave like a particle, as opposed to a wave or some macroscopic object like a star or something. And this range of cross sections is exactly the range that's been probed by all the experiments that we've thrown at dark matter so far. So it is in this space that the rest of this talk is going to be based on, where I'm going to talk about experiments to probe the microscopic identity of dark matter in the space of cross section versus mass. And in particular, I'm going to be talking about a couple of experiments. The first one is going to be based in space. The basic idea is that dark matter could set certain kinds of stars on fire, and this fire could very well be observed by upcoming telescopes, especially those operating in the infrared emission range. The second experiment that I'm going to propose is going to be based on Earth. In particular, it's going to be based in Sudbury, Ontario, in Canada. And the basic idea here is that while we've been looking for dark matter with the direct detection technique, using meter scale detectors, dedicated meter scale detectors, the time has probably come for much bigger detectors that are like 1,000 times bigger in volume, namely neutrino detectors, such as SNO+, to join the hunt if we can repurpose them in a clever way. Okay, so those are the ideas that we're going to be exploring in this talk.
So,
Okay.
Nirmal, can I
Yes,
ask
please.
one more question? And I'm sorry, because
Yes.
I will have to leave
Of course,
soon
of course.
as well.
Yes.
If you go back just 2 slides to your cross-section versus mass, yeah. So, well, not shown here, but it's there and it's very close now, is what's called the neutrino floor, right?
Indeed, indeed. Yeah.
So I don't know if you will talk about this later, but I'm wondering about these techniques that you're proposing, whether they allow scope for us to go down below the neutrino floor in probing these cross sections and masses.
So, okay. So, Jim, since you are going to leave soon, I'm going to give a spoiler here.
Sorry, everyone.
No worries at all. I would absolutely. So, the neutrino floor is about 2 orders of magnitude below the gray curve here. And the first technique that I'm going to talk about will easily surpass the neutrino floor for a wide range of masses.
Okay.
The second technique that I'm going to talk about will have no neutrino floor associated with it, because for neutrinos can scatter at most once in the detector as they pass through them, whereas the very definition or the very technique that I'm going to be talking about looks at dark matter that would scatter multiple times in a detector, and there would be no neutrino floor at all associated with that technique.
Okay, so that's very exciting, given the known limitations from these types of detectors that you are listing on this slide. So
yes,
yeah, okay.
Exactly, yes.
All right. So I this is probably the last time I'll speak. So I will watch this back, and I may mail you a few questions if I have them.
Absolutely.
Okay. So yeah, thank you.
Complete pleasure. Thank you. All right. So let's jump into the first experiment. The proposal here that I made with my excellent collaborators here, accepted at physical review letters, is that you could use neutron stars as your scattering target in this reverse Rutherford experiment. Now, a quick refresher on neutron stars. These are degenerate remnants left behind by core collapse supernovae. These are sometimes described as giant nuclei in the sky. The little blobs I've drawn here are basically energetic electromagnetic jets that are spewed out from the poles of the neutron star, so that when the neutron star spins around, this beam sweeps around the Earth, sweeps into the Earth like a lighthouse at regular intervals, and you could discover these neutron stars as pulsations, and that's why some of these are also called pulsars. Now, if you think of the neutron star as your detector, dark matter detector, then the detector properties are that neutron stars are 20 kilometers on an average in extent. Their densities could go as high as 10 to the 15 grams per centimeter cubed, which well exceeds nuclear saturation densities. And in fact, neutron star cores are known to be some of the densest objects known to man in the universe. And as for their temperatures, most neutron stars are pretty old, because most stars that have ever been formed are pretty old. And so a typical neutron star is 100 million years to 10 billion years old. And those neutron stars are expected to have cooled down all the way down to 100 or just 100 or 1000 Kelvin, because there's nothing inside that there's no fusion or anything going inside to power them. It's only quantum degeneracy pressure that's keeping them from crushing under their own weight. So not only are neutron stars giant nuclei in the sky, but they're also giant snowballs in the sky as far as temperatures are concerned. Now, the idea that we proposed is actually pretty simple. Ambient dark matter would smack into these neutron stars, right? And if you calculate what the flux of the smacking in is, as long as the cross-section for dark matter to hit neutrons satisfies the condition that the mean free path of dark matter through a neutron star is smaller than the radius of the neutron star, what you find is that any dark matter particle that passes through it would get gravitationally captured and transfer all its kinetic energy to the neutron star. And under equilibrium conditions, the luminosity of the star from this dark matter smacking into it would be equal to the power of the kinetic energy of dark matter that you pour into the star, right? So this mechanism we have dubbed dark kinetic heating. And if you actually do the calculation for a typical neutron star and try and equate the luminosity to the kinetic power of dark matter given the density and speed of dark matter in the solar neighborhood, what you find is that dark matter should heat up all neutron stars uniformly to a temperature of about 1750 Kelvin. Okay. Now, there's an exact analogy to the mechanism that I just described, and that is, this is exactly how you keep your soup hot, right? If you want to maintain the temperature of your soup, what you want to do is to stop it from cooling, and the cooling rate for if you model it as a black body is given by 4 powers of the temperature times the area times the Stefan-Boltzmann constant. And if you want to keep the temperature, if you want the left-hand side of this equation to be 0, you want to put in an external power source, for example, a fire. And if you tune the fire's power to be equal to what's on the right-hand side in the first term, then you keep the soup from cooling down. That's exactly what's happening here, except the external power is now, the fire here is coming from dark matter itself. Now, as you could see, this calculation, this idea is so simple that every time I think about it, I wonder why Zwicky himself didn't actually do this calculation in the 1930s. Because Zwicky not only proposed the existence of dark matter, but also the existence of neutron stars just the year after neutrons were discovered by Chadwick. And so he could have answered himself the question, how hot can my dark matter keep my neutron star? But I suppose Zwicky didn't really know what the ambient speed of dark matter is, because there were no good measurements back then. And although there was one measurement of the dark matter density back then, it was not really well publicized. So not knowing these inputs, Zwicky probably didn't have the means to calculate the total external power of dark matter falling into the neutron star. Anyway, we are much luckier in that respect. And what we could infer from a particle physics standpoint from this mechanism is that if we were to see neutron stars burning at this temperature or not burning at this temperature, you could set a sensitivity or a constraint in this space of cross-section versus dark matter mass. And what you find is that this huge space indicated by the green region could already be constrained by observing a neutron star that is colder than 1750 Kelvin. Okay, and if you notice, this region goes all the way down to 10 power minus 45 centimeters squared, and then you lose some sensitivity versus mass at high masses, because now you need to scatter multiple times in the neutron star to capture it. At low masses, you lose some sensitivity because of Fermi degeneracy, which means the momentum transfer that you give neutrons in the neutron star is not enough to capture. But otherwise, it's still a pretty huge chunk of this parameter space that you could already be sensitive to.
Nirmal,
yes.
Can I ask some stupid questions? So how do you get this number 1750 Kelvin?
Right. Sorry, maybe I glossed over it a little bit. The number comes from setting the luminosity of the neutron star given by, say, this formula down here. So you can see my cursor, right?
Yes.
Okay. So given by the Stefan-Boltzmann formula, you set that luminosity to the kinetic power, and the kinetic power is nothing but the kinetic energy of dark matter times the instantaneous flux of dark matter falling into the star. And since you already know the density and speed of the dark matter, and since you know that dark matter would accelerate to the escape velocity of the star as it falls in, you could easily calculate the kinetic power, and you set it to the luminosity, you get this as the temperature. Did that answer your
Okay.
question?
Yeah, kind of, sort of. But what prevents the dark matter from being gravitationally bound to the neutron star? And
Oh, it is indeed bound. Sorry. Yes, it is bound to the
okay,
neutron star. When this happens, it
okay,
transfers its
so
kinetic energy, and now because it's now caught in the gravitational well, it is bound to the star. Yes, but that is not the effect that we could actually probe. What we could probe is how it heats up the star.
yeah, okay. So the picture is not something like it just simply goes through the star. It's rather that it is loses its kinetic energy and it spirals inside and then gets bound to it, and in the
Indeed,
process it loses its kinetic energy and transfers it to heating up the neutron star.
indeed, that is
I see.
exactly the picture. Yes.
Okay, thanks.
Yeah. Okay, so okay, so for in the cross section versus mass space, this is the region that you could probe. Now there is a fast one that I pulled here. Now 1750 Kelvin is not something that we could already measure with existing telescopes because our telescopes are just not sensitive enough to do that. So what we need to do, what we need is future technology to actually make this a viable probe. And here is a reasonable trajectory that we proposed with guidance from some astronomers on how to do this. So since neutron stars are also pulsars, we could first discover some old, cold, isolated neutron stars that are nearby using radio telescopes, such as CHIME in British Columbia, not far from here, and FAST in China, which both of which are already operational. And it's possible to discover a lot of neutron stars this way because standard estimates tell you that just within the local 50 parsecs, about 100 old cold neutron stars should be abiding. And once these are discovered, you ask for upcoming infrared telescopes, which are designed to look for example, exoplanet atmospheres. You ask them to stare at these particular neutron stars and give us a constraint or a measurement of the thermal luminosity of these neutron stars. So the telescopes that we have in mind are James Webb, which hopefully comes online later this year, or the Extremely Large Telescope, which might come online in 2025 and placed in Chile, or the 30-meter telescope. If all goes well, it should come up in Hawaii in 2027. Okay, and we've already been talking to 30-meter telescope astronomers. 2 years ago, there was a 30-meter, the first collaboration meeting of 30-meter telescope actually happened in Mysuru. And one of my collaborators, Joe Bramante, actually flew to India to attend this collaboration and convinced astronomers to do this because it's very important for dark matter searches. And I'm happy to report that all the astronomers that we've talked to are actually enthusiastic about this idea, and hopefully we'll bring this to fruition. Now, that's the basic idea. And while these telescopes are coming online, I've been working on some important variations on this theme. So for example, I think it's a very important question to ask if we should actually refrigerate dark matter inside these neutron stars to see its effects. And what I mean by that is, once you gravitationally capture dark matter, as Ian had suggested, it's not clear whether the distribution of dark matter in the neutron star, the purple circle here is the neutron star, the black is dark matter. So it's not clear if the distribution looks like this or the picture on the right, if the dark matter sinks all the way to the center. That's an important question because what I had described so far is what I would call the minimum signature of dark matter heating up neutron star, where dark matter accelerates, falls in, hits up the neutron star by transferring kinetic energy. But there could be a second mechanism that adds additional heat to the neutron star, namely, if dark matter sinks to the center of the star and undergoes efficient annihilations, then the annihilation products could further deposit energy into the star and raise the temperature even further. And that could help these telescopes. They could bring down the observation times down by a factor of 10. And they would love that because observation time is exactly equivalent to tax dollars. So it becomes a very important question to ask whether dark matter actually thermalizes with the neutron star and whether it collects into a small ball in the center or not. And with my collaborators, what I find that it is, of course, a highly model dependent question. So the answer could be either yes or no, depending on which model of dark matter that you're talking about. But in the interest of time, I'm not going to go into the details of this, but you could look up our paper here. Another important
Yeah,
question.
Nirmal, I
Yes.
just want to
Yeah.
ask you something here, because so people are also trying to understand the equation of state of QCD matter from
Yeah.
this gravitational waves. And here, then if the first scenario is correct, then actually it will significantly modify all these things,
Right.
right?
So what the cartoon doesn't say here is, given the density of dark matter, which is just 0.3 GeV per centimeter cube, even if you collect dark matter over 10 billion years, it would only make up a very small fraction of the star's mass, this fraction being 10 power minus 15. So the dark matter that you collect here would not actually affect the equation of state of the neutron star. That's actually a very good question. This was something that was bothering me as well. But no, you don't collect enough dark matter to affect anything about the macroscopic properties of the star, especially not the equation of state. For that to
Ah,
happen,
okay, that's
you
good to
need,
know.
yeah, you need an order one fraction of the neutron star to be dark matter. And
Maybe
there are
both good and
other,
bad to know. Okay,
yes,
I see.
indeed, yes, exactly.
Okay.
Okay, so these are great questions. Please keep them coming. So the other important question that we asked ourselves with other set of collaborators in UC Riverside is, well, the calculations that I made, that I showed you in the previous slides, pertain to dark matter scattering on nucleons, in particular neutrons in the neutron star. But a neutron star is not made of not just neutrons, despite its name. There's also a huge fraction of up to 10% fractions of electrons and muons and protons, because you cannot escape having these just from the beta equilibrium. Okay. So maybe dark matter doesn't like to interact with neutrons. Maybe it likes to talk more with electrons and muons. In that case, we might be barking down the wrong scattering target. So it's important to also derive the sensitivities for dark matter scattering with these other targets. And that's what we did. The one subtlety here is that we had to treat scattering with electrons more carefully, because electrons are very relativistic in the star. Their Fermi momentum is much higher than like 150 or 300 times higher than their mass. So they're deeply relativistic in the star. So we had to put in the correct relativistic kinematics and put in the correct Fermi Dirac statistics by shifting frames and so on, which we did and found pretty good sensitivities. But the variation that I want to talk about in this talk is this one. Namely, the approximation that I made in the previous slides is that the core of the neutron star, which extends to about 10 kilometers in radius, I assume that the core makes up most of the star. Sorry, I assume that the dark matter scatters with the core of the star, which makes up most of the star. However, the core, as Ayan had touched upon now, is exactly the most uncertain part of the star, because we don't really know what the equation of state of matter is, or equation of state of high density QCD matter is at these supernuclear densities. So we don't really know what governs the dynamics of dark matter scattering in the core of the star, especially the inner core. So that then brings up a frightening question. Have we been barking down the wrong stellar region in all this? Maybe we should be thinking about the crust of the star and not the core of the star. And that is what we explored in this paper. Um, and to introduce you to the results, here's a quick review of the structure of a neutron star. This is a cross section of the neutron star. So there's this thin crust which extends to about a kilometer. On the top of the crust, there's a very thin atmosphere and an ocean, but we're not going to be concerned about that here. There's also an inner core and an outer core. And as I was saying, despite its name, the neutron star core may not be made of neutrons. Maybe it's made of quark matter or meson condensates and so on. And since we are now, okay, sorry. So because of this uncertainty about the composition of the core, it becomes very important to check what the sensitivity of dark matter capture is with just the neutron star crust. And that makes it important for us to understand what the crust is made of. So here is a cross section of the crust. The crust is divided into an outer crust and an inner crust, depending on the density at which neutrons start dripping out of nuclei. The outer crust is made of heavy metals to begin with, but as you keep going down, densely packed nuclei. As you go into the inner crust, you start having free nuclei, which form neutron superfluid. And then the most interesting part is that as you go to the bottom of the crust, the densities here are so huge that due to a lot of competition between short-range nuclear forces and long-range Coulomb forces, the nuclei and nucleons in this region are no longer spherical in shape, but form all sorts of interesting configurations, such as gnocchi, spaghetti, lasagna, bucatini, Swiss cheese, and so on. So this region is known as a pasta phase. And that plays a very important role in our calculation. Okay. Now, one thing to remember here is that the deeper you go into the neutron star, even the crust, our knowledge of the structure of the neutron star becomes more and more uncertain. Our knowledge comes more and more from simulations and semi-analytical models and so on, and less from empirical knowledge. Which means even though you are getting into denser regions so that these regions capture dark matter better, these results must be taken with a larger and larger grain of salt. Okay, these results become more and more dubious. So with that in mind, let's look at how scattering on pasta proceeds. I might probably rush through this a little bit. What we found is that the way to treat pasta is to for dark matter moving in at low momenta, is pertaining to dark matter with low masses. You have a many body effect where the scattering on pasta is given by a response function times the scattering cross section with individual nucleons, and the response function has been simulated by various groups, so we took them to use in our calculation. At high momenta, the way dark matter gets captured in the neutron star is via quasi-elastic scattering, by which I mean dark matter hitting on these nuclear pasta structures and ejecting nucleus, and only such processes transfer enough momentum for dark matter to get captured. Now, putting all this information to turn into sensitivities in our beloved cross-section versus mass plot, this green band is the cross-section sensitivity of dark matter scattering in the pasta layer in neutron stars. It's a band as opposed to a line because this captures the uncertainties coming from the various equations of state that people have proposed in the market for high density matter in the neutron stars. For comparison, I'm also showing here limits from the terrestrial direct detection experiments that we saw in the first few slides. And what you could see is that at low masses, there is like no experiment that could do as well as the pasta layer in neutron stars. And at high masses, our limits, well, these are not limits, our sensitivities are comparable to the experiments that are meant for that are designed for high mass dark matter. But this is only for a 1750 Kelvin neutron star. It's also possible to set constraints with neutron stars that are colder than that. And all that means is probing smaller and smaller cross sections. So if telescopes are sensitive enough to probe colder neutron stars, then you could move this line proportionally down. And you might start beating the sensitivity of xenon 1 ton. And you could also already, with just the pasta layer, you could already beat the neutrino floor that Libby was mentioning. Okay, so much for neutron stars. And to summarize this part of the talk, neutron stars are very promising probes of dark matter. And if we can get our hands on upcoming infrared telescopes in a time scale of 5 to 10 years, we should start seeing very important or very extensive, we should start having very extensive results about dark matter scattering. Okay.
Just to summarize, so your basic point is that although it doesn't affect the mass, it will affect the temperatures at the various layers.
Yes, exactly. It will affect the temperature of the neutron star, and we don't know which layer. We may not immediately know which layer of the neutron star is doing the work. Maybe somebody, and there are experiments that are trying to nail down the equation of state. Maybe somebody will find what the equation of state is. Then we might know whether the heating is coming from the crust or from the core.
Yeah, but the way you see it is some modification of the mass radius relation after all, or that also
No,
doesn't get
the way
modified
you see it is through the infrared telescopes, and you
through the
count
infrared
the
telescope.
exactly. You just measure the thermal luminosity of the stars. That is, you count the photons
Okay,
coming
as
from the,
simple as that. Okay, I see.
as
Just
simple as
simply
that.
count the
Exactly.
photons. Okay, infrared
Exactly.
photons that you, and you
Exactly.
see match it to some thermal spectrum.
You match it to a thermal spectrum that is
Okay.
predicted by us. Exactly.
Okay, very good. Thanks. Yeah.
Yeah. Okay. So now that's the future promise. But as I mentioned, we've already been probing dark matter scattering in terrestrial experiments. And we've been doing this since 1985 through these direct detection experiments. And great swathes of cross-section versus mass space have already been constrained, right? And it all began when Drucker and Studolsky proposed detecting not dark matter, but neutrinos in the channel of coherent elastic scattering. And this idea inspired Mark Goodman and Ed Witten of string theory fame to propose the direct detection experiments, the exact same technique, but now you look for ambient dark matter and look for them in coherent nuclear recoils. Now, when Goodman and Witten proposed their experiment, taking the numbers in their paper and turning it into a plot, what I find is that the sensitivity that they were thinking about looks roughly like this in the cross-section versus mass space, where they could go down to about a GeV in mass and up to about 10 power 13 GeV and probe cross-sections just around the vicinity of 10 power minus 42 to 10 power minus 22 centimeters square. Okay, that was back in 1985. But today, experiments have grown and become so sensitive that the net sensitivity looks like this. Here's kind of all the experiments that we've thrown at dark matter scattering. And as you could see, our sensitivity or our constraints have grown by many orders of magnitude in all sorts of directions, right? But that's not all. These detectors have become so advanced that they have transcended their purpose. And now you could use them to detect not only dark matter particles, but all sorts of interesting theories. For example, these detectors are now so sensitive to the tiniest fluxes of particles and the tiniest energy depositions that you could use them to detect supernovas from the next galactic use them to detect neutrinos from the next galactic supernova in our galaxy, in the Milky Way. Okay. So, and that could that could actually very decisively resolve some existing debates on the explosion mechanism of supernovae, in particular type 1a and failed core collapse supernovae. The the other thing that could be done here is you could also look for with these experiments, you could look for the decay products of hydrogen decay, a process that is predicted by well-motivated theories today. In particular, last year, the xenon 110 experiment using liquid xenon time projection chambers observed an excess of around 3 to 4 sigma in electron recoils, especially at low energies. And I realized that if all the hydrogen in the oceans of the Earth were decaying right now with a small branching fraction to these exotic particles, then these particles have just the right flux and just the right energies to explain this excess. And happily, this proposal was accepted at Physics Review Letters and published as editor suggestion. But coming back to dark matter detection, sorry. So coming back to dark matter direct detection, here's again all the constraints in the cross-section versus mass space. And one obvious thing you would have noticed is that these constraints are not infinite, that they are bounded in all 4 directions. And the reason they are bounded is there is something that's limiting these experiments in each of these directions, right? So if you want to make progress in dark matter direct detection, I think it's important to understand what exactly are the limitations of these experiments in each of these directions. So let's look at them one by one very quickly. Now let's look at the vertical down direction. As you go down in cross sections, dark matter becomes more and more ghostly. So it just passes through your detector without scattering on anything. And that limits your experiment in this direction. And the way you would fix that, as experiments do, is to make your exposure larger. Basically, you try to make your detectors bigger and bigger and wait for longer and longer times until one of these dark matter particles hits your detector and you see a signal, right? Now in this direction, in the left direction, as you decrease your dark matter mass, and especially when your dark matter mass becomes smaller than your nuclear target mass, dark matter now behaves like a bug hitting a truck. That is, it doesn't produce enough recoil energy to trigger your detector above its inherent threshold, right? So dark matter basically behaves like a powerless particle, and the way people try to fix that is to improve on the energy threshold technology with electronics and new exciting results from material science and so on. Now, up in this direction, as you go to higher and higher cross sections, what happens is at these very high cross sections, dark matter now scatters not just with your detector, but with whatever surrounds the detector also. So it scatters with the surrounding, say, the crust of the Earth or the atmosphere or the shielding of the detector so much that it gets pretty tired by the time it comes to the detector and doesn't trigger the detectors above threshold. Right? So this is the overburden effect. And the way you fix that is you try to move up the detector in its location on Earth. And in particular, what I mean by that is you try to put your detector on the surface of the Earth so that you try to reduce the crust overburden, or you put your detector in the upper atmosphere or in outer space in a combination of balloons, rockets, and satellites, as done by these experiments. And finally, in this direction, as you go to pretty high masses, since you only know the mass density of dark matter and not the number density, as you go to higher and higher masses, you know that the number density of dark matter becomes smaller and smaller. So out in the halo, your dark matter is just diluter and diluter until you reach a point where there is no dark matter particle ever that has passed through your detector in the runtime of the detector, regardless of whether it's scattered or not. Right? So dark matter is so rare that you just don't see it. And that sets the limitation here. And what I want to mention here is that while the other three directions are being very actively pursued by experimentalists, this direction for some reason has been completely forgotten. In fact, the line that I'm showing you here at 10 power 16 GeV was drawn by the Dama experiment way back in 1999. And then there's no underground experiment that does this anymore. It's just been forgotten, probably because people are now looking for WIMPs. So just to visualize what that means, the region that experiments are actively hunting right now is around the electroweak scale, corresponding to WIMPs, or 100 GeV in mass. That corresponds to a number density such that the average interparticle spacing of dark matter is about 7 centimeters. Whereas at the mass that Dama had set this limit at around 10 power 16 GeV, the interparticle spacing is as large as 4 kilometers. That's how rare dark matter we are talking about here. Okay, so what do we do about this? And more naggingly, what if dark matter is actually hiding here in the rare frontier of dark matter direct detection? How do we go catch it? Well, that idea has a lot of theoretical appeal because 10 power 16 GeV is exactly where what we call the grand unification scale. This is exactly where there are ubiquitous super heavy stable states predicted by theories of grand unifications of forces. And also, there's a lot of mechanisms proposed in the market, very attractive mechanisms for making these heavy stable states in the early universe. I don't have time to go into all of these now, but probably my favorite is the first one mentioned here. You could make these particles through Hawking radiation from primordial black holes. So sorry, Ayan, how am I doing on time? How much time do I have left?
Yeah, you're doing excellently on time. So
okay, fantastic. Okay.
You certainly have 10 minutes, actually 12 minutes.
Okay, great. Okay, good. Now, when Dama set their limit, the experiment setup consists of 10 centimeters, a crystal of linear dimension 10 centimeters, and they waited for about a year. That set their exposure, and that's what led them to set a limit at 10 power 16 GeV. Whereas today, our experiments have become much bigger. Now we use meter scale experiments, 10 times bigger in linear dimension, so 1,000 times in volume. So does that mean our dark matter detectors today can already hunt the rarest huntable dark matter? That was one question we asked, and wrote papers with experimentalists Ben Broerman and Raphael Lang, and their respective experiments, PICO and Xenon 110, are already looking for the signature. In the meanwhile, I also joined the Deep 3600 experiment based in Sudbury, Ontario, in Snow Lab, using the liquid argon, for its detected material to look for the highest mass dark matter. And there's an ongoing search, which I'll talk about in a minute. Another question that we asked was, well, these are dark matter detectors, but we don't know there are much bigger detectors around in the form of neutrino detectors. Could we do something to them? Could we repurpose them, or could we tweak them to also join the hunt for dark matter? That way, you could now search for even rarer dark matter than could be searched for with the dark matter detectors. Sorry, that was a mouthful, but I hope you got what I meant. So the answer to the first question at first glance is, of course, yes. You could, because the detectors have become so much bigger. Of course, now these detectors could look for dark matter that's much higher than the 10 power 16 GeV limit. Be it the liquid xenon time projection chambers, such as Xenon 110, Lux, or Panda X, Deep 3600, which I mentioned, or bubble chambers like Pico 40. So does that mean these experiments have already automatically set constraints without them knowing it, and we just have to redraw those curves? No, not so fast, because there's yet another aspect to direct detection that must be taken into account. And that is the following. So here's a cartoon of the cross-section versus mass plots. And what you see is that as you go to higher and higher masses, you also necessarily probe higher and higher cross-sections because the number density is falling, right? Until what happens is you hit a point where the cross-section is so high that you don't expect dark matter to scatter just once in the detector as it goes through the detector. The dark matter has to necessarily scatter multiple times in the detector, and that's a completely different beast to an experimentalist, as opposed to the WIMP signature, which involves only just one hit as the dark matter passes through the detector, right? So now you have a track, and you have a lot more energy deposition, and these are exactly the kinds of events thrown away by the experimentalists before they start doing the analysis for WIMPs. So necessarily to probe the high mass frontier, you also have to get into multi-scatter signatures. Okay. Now, how do you look for multi-scatter signatures in these experiments? Various experiments. So Xenon 110 is doing it in a different way. Pico, my friend Ben Broerman, has already done the search, but won't tell me the result. He's done it in a different way. But I can talk a little bit about the experiment that I'm involved in, the Deep 3600 experiment at Snow Lab. I'm on the analysis working group consisting of these very fine physicists. And I'm very excited that the unblinding of the review for the unblinding of the data is coming up in 12 hours. So I'm just going to go to sleep after this talk, wake up, go to that meeting, and I'm going to hear whether they're going to open the data for us to look for dark matter. So it's a very exciting time for us. A back of the envelope calculation shows you that if you use the Deep 3600 experiment, it being the largest dark matter experiment on Earth right now, with a diametric extent of 130 centimeters, it would actually become the first dark matter experiment to reach the Planck mass with 1 year of running. Okay, so that's something we're very excited about, because we don't really know what experiment could actually touch the Planck mass.
But Nirmal, are you looking for how many multiple scatterings are looking for? Are they many enough to leave a track, or it would be a more complicated kind of analysis?
So we are looking for all sorts of hits. For example, we're looking for 2 hits. We're also looking for 5 hits, which is a different analysis. We're also looking for 1,000 hits, which is a completely different analysis. So we're looking at various regions that give you different kinds of signatures.
So that for that you need
So,
to
and
model
that,
the detector in a very precise way, right? You need to a very precise understanding of the
exactly. And
detector
thankfully,
physics.
exactly.
I see.
Thankfully, since I'm doing this with experimentalists, I'm the only theorist on this experiment.
Okay, I see.
Since these are all experimentalists, I'm pretty sure they know the
I see.
detector
I see. Because detector physics is another
million times
kind of
better than me.
yeah.
Absolutely,
Okay.
exactly. It's been,
Yeah, I
for me,
see.
it's been just an educational experience. I just sit on their meetings, and if they have a theory question, they ask me, and and then they
I
ask me,
see.
how do we write about this? That's all. That's kind of mostly what I do. I'm a consultant, but it's been all very educational for me, I have to say, for this
Okay.
of working with experimentalists. Now, I'm not at liberty to go into the details of this search because they won't let me tell you before the data is unblinded or before the paper comes out. But I am at liberty to tell you that what we are doing here is a waveform analysis. You look for the exact waveform of energy deposition in your detector, and you use some special variables that they have been using for WIM searches, but now you modify them, and that gives you a very good handle on how to look for multiscattering dark matter. Okay, so here's a second question. The second question is, could there be other bigger detectors that can join the hunt? And as I spoiled it for you, um, neutrino detectors, and in particular detectors like SNO+ could join the hunt for dark matter. And how do you do direct detection with these detectors? Well, to begin with, the most suitable detectors are those that have liquid scintillators in them. In that case, the mass sensitivity is given by the total cross-sectional area of these detectors. And as you could see from these two pictures, sorry, here's the xenon wanton experiment on the left and the borax-xeno experiment on the right. Both are in the Gran Sasso National Laboratory in Italy. With physicists for scale, you could really see how big the detector on the right-hand side is compared to the left, right? So cross-sectional areas are 100 times bigger, and that means you admit dark matter flux is 100 times greater, and thus you are sensitive to dark matter masses that are 100 times greater. Now, as for the cross-section sensitivity, all you need to do is to satisfy the selection trigger of these detectors. Basically, you need to satisfy a certain amount of energy that is being deposited in the detectors within a certain time window. And that can always be satisfied by cranking the cross-section up so that your dark matter scatters multiple times in the detector, right? And I want to illustrate this with SNO+ as an example, also my favorite liquid scintillator experiment. Here's a model of SNO+, a scale model at Snow Lab, a picture that I took when I visited Snow Lab a couple of years ago. And here's a selfie that I took on a photomultiplier that was out for repairs, 2 kilometers underground, just outside the SNO+ detector. So the reason I visited Snow Lab was to take part in, so I was invited for the SNO+ collaboration meeting after having published this paper to talk at their meeting about dark matter searches. And we had a lot of exciting and fruitful conversations. And the experimentalists are really excited to do this search. They really have they really have been thinking about the software trigger to do this and so on. The data acquisition system guys have been fantastic in their communication with us. And that is the story that I want to share with you now in the next maybe 2 or 3 minutes. So the one really exciting thing about doing this with SNO+ is that it's represented on this plot, where the fiducial area of SNO+ is about 1 million centimeters square, right? Which is like 10 times, 100 times larger than dark matter experiments. And because of that, if SNO+ were to run this experiment for just 3 hours, right, then they would already be setting the world-beating limits on dark matter mass. They would already surpass Dama's 1999 bound with just 3 hours of running. And then if they were to run it for just 10 days, then they would be able to start beating the sensitivities of, say, xenon wanton with 1 year of running. And then if they were to run for a year, they would easily surpass the Planck mass, and 10 years even 10 times larger than that, and so on. So that this was a plot that really caught their attention, because they just need to run it for 3 hours. They don't even have to do it continuously. And the signature here um, basically is a continuous deposition of photoelectrons over the transit time of dark matter, which for a detector the size of SNO plus is 10 microseconds. Okay. Another neat thing here is that since we are talking about dark matter that is psychotically heavy, such as 10 power 16 to 10 power 17 GeV, scattering on say carbon particles that are about 10 GeV in mass. Because of that, the dark matter particles are just going to go straight through with very little angular deviation. So you could exploit this collinearity with their excellent vortex reconstruction and timing, the nanosecond timing that they have in the detectors. Right. So this is a smoking gun of dark matter in these experiments. And to illustrate very quickly how signals might look like, up here I'm showing a couple of 10 microsecond windows with the dark matter signal of about 10 power minus 28 centimeters squared cross section. And with 10 microseconds, you might expect these many hits in this window, okay, about 30 or 40 hits. Whereas the leading background to these searches comes from what is confusingly known as dark counts, but basically thermal agitations in the photomultiplier tubes of these experiments. And the dark count rate in these experiments typically is such that they look only as noisy as this window. Okay, so clearly you could distinguish dark matter from a dark matter window from the dark count or the PMT window, PMT thermal noise window. And the secondary background comes from beta decay of carbon 14, um, which is an abundant isotope in these liquid scintillators. But even then, they appear only once in 100 windows, and then they only make one little blip, such as here. So even if you take into account the look elsewhere effect and look at all the windows over, say, a 10-year period, there's only one window in this entire 10 years that would look like a dark matter signal. So it's very easy to scrub out the background and say something very nice about dark matter. Okay, so we turned all that information into future sensitivities. It's a busy plot, but again, this is on the cross-section versus mass plane. In the interest of time, I'm just going to describe a couple of curves here. Basically, our curves given by these blue lines. With the existing threshold at Borexino, you could now probe cross sections at 10 power minus 26 centimeters square and above. But then we also proposed an improvement to the trigger. If they were to implement that, they could gain in sensitivity by a factor of 100. And with 10 years, SNO Plus should be able to set a mass limit at 10 power 21 GeV. So, okay, there's a little more to the story. You could also, since you are now reconstructing tracks, you could reconstruct the dark matter velocity vector and start telling, using a terrestrial experiment, you could actually start telling information about how dark matter is distributed in the galactic halo. You could infer its speed, its escape speed, its dispersion speed, anisotropies, and so on. But I'm not going to go into that in the interest of time. So I'm going to go to my summary. So let me summarize my talk with these plots. So in the beginning, just before the reverse Rutherford era, we really don't know whether dark matter had any interactions at all with nucleons. So this parameterizes our ignorance. And then in 1985, thanks to Goodman and Witten, we entered what I call the reverse Rutherford era of dark matter. And here was the sensitivity that they had proposed with their primitive detectors. And today we are in the thick of the reverse Rutherford era with so many different experiments, so many advancements, so many techniques and materials and so on. And we have increased our sensitivity to this region, this pretty huge region. Now, in the near future, if experiments, well, there are a few experiments that are doing already, but in the near future, if future experiments also take up the multi-scatter idea, and if neutrino detectors could be repurposed to look for dark matter, then here is the extra space in the high mass frontier that we could be sensitive to. And then in the middle future, hopefully we will find good candidate neutron stars to stare at, and using infrared telescopes such as James Webb and the extremely large telescope and the 30-meter telescope, we should be able to say something about the thermal luminosity of neutron stars. And if we find neutron stars to be shining colder than 750 Kelvin, then all the space goes. Okay. Or to be more optimistic, we could find a lot of neutron stars shining at just the right temperature, and then we'll definitely know that dark matter is living somewhere in this green region. So now all this gives me a lot of optimism, because now I'm really hopeful that with all this advance in technology and with the synergy of working with theorists, we are not far away from getting close to pinning down the identity of dark matter, and maybe learning something more about the friends of dark matter in the dark sector, and learn something really cool and new about this completely new subatomic particle that none of us have dreamt of, and learn something really profound about our universe. Thank you very much. Happy
Hi,
to take
Nirmal,
more.
it was great. So thanks for this wonderful talk, and it was especially a pleasure to listen to you for two reasons. So firstly was that you have given so many nice original ideas that has led to new proposals for new experiments. And secondly, I think also that you have been able to collaborate with astronomers and experimentalists. That's quite rare, I think. So, so essentially,
Yes,
I have just two comments before I open the question. So you can answer my comments
yes,
later. You should first
definitely.
answer the other questions. My first comment would be just to, I'm just curious to know how much of your time at IIT have helped you in shaping your career, number one. And number two would be related curiosity. I think there have been a lot of new kinds of proposals for dark matter detectors, where you could actually marry your first love with your second love, or your present work. Like
Yes,
they're really trying to use a lot of condensed matter, new kind of condensed matter, solid state phenomena and devices. So that you can actually marry some condensed matter theory with this dark matter searches, perhaps. But first, you should answer other people's questions and get back to this.
okay,
Okay, so
definitely.
time
Yes,
for other questions now.
thanks very much for
Can I
the.
ask a quick question? As a
Yes, please.
non Nirmal, so very nice talk. I really enjoyed it.
Thank you.
Can I just ask a very? I was disconnected for a short time, so maybe if you have already touched upon this, then I'm sorry for asking it. What exactly goes into your calculations? I mean, in the sense that so in the neutron star part, the equation of state for the neutron star, and this you essentially take various equations of states, or
Okay. So, okay.
and what I
So,
mean, what about
yeah.
the interactions itself? Is it as asked earlier? Is it purely gravity type? What?
No. So,
Okay.
okay. Sorry. Let me go back to the pertinent slide and try to answer your question here. So in the first part, where I approximate the neutron star to be just neutrons, over there, the only thing I'm assuming here is that dark matter scatters with the star. And then I take the flux. So the one thing that goes into the calculation is the flux, as I show here, the flux and the kinetic energy that gives you the kinetic power. And if I assume that dark matter scatters, the next step is to check whether the scattering is enough to get captured in the star. And yes, it does get captured. You'll find that it does get captured. And then you ask, then what is the minimum cross-section that I need for it to actually scatter?
Okay.
When I do that, I get this. The cross-section, for the broad audience, I just want to remind that the cross-section is defined by that's just when you have the mean free path is equal to 1 over the cross-section times the number density of the material that you're scattering into. So if the mean free path is smaller than the neutron star radius, then I know what the minimum cross-section should be.
Okay.
And I find that cross-section is this.
Wow.
And that's enough, because I know that once if the dark matter scatters somewhere in this region, then it gets captured in the star. And I know for sure that, I don't know for sure, I calculated it. after calculation, I know for sure that the kinetic energy is all transferred to the star, and that kinetic energy is radiated as heat.
Right. Right.
So that is all I'm assuming in the first part. But in the second part, I'm questioning that assumption.
Right.
In particular, this one, the third question, because I'm not sure that the star actually is made of neutrons. Because nobody is sure, because we don't know the high density equation of state.
Right.
But we do know what the crust is made of. So at the least, I want to check what now the cross section for scattering with the crust is, given the density and extent of the crust. Then I find that the sensitivity is this. Maybe I should have shown a comparison plot, but now to guide your eye, the cross section is actually now 4 orders of magnitude higher than the one that I showed in the previous one.
Nice.
So that's all that goes into my calculation. The one extra bit here is that because we even in the crust, we don't really know what the equation of state is. So I'm using all the equations of state that I could get hold of in the market and varying them, and that gives me this uncertainty band.
Okay.
So, yeah.
Thanks.
Nirmal, is the temperature in a neutron star expected to be the same, or it will be different in the crust and the core? And so when you're talking of temperature, what is this temperature you're talking about?
Yeah, so that's a very good question. So the crust and core temperatures usually are not the same, but that is true for neutron stars that are still young. By young, I mean younger than about 1 million years. When they are still cooling via neutrino emission, you don't expect the crust and the core to be of the same temperature. But I'm looking at neutron stars that are well past that, and they have nothing going in them. They're truly dead. They behave like a very nice smooth black body. And so whatever heat you put into them, the crust and the core thermalize very quickly. We calculated that the thermalization happens within a year or so. And so it doesn't matter whether you're talking about the crust temperature or the core temperature. At the end of the day, you just look at the surface temperature. That is guaranteed to be the core temperature as well.
And what are the general ranges of temperatures of neutron stars, observed neutron stars that we know of?
So the observed neutron stars, there's a huge sampling bias in them. We have observed order 1,000 neutron stars so far, whereas we do know that there's like 10 power 9 neutron stars in the galaxy. And the 1,000 neutron stars that we have observed are all younger than about 10 or 100 million years, because our telescopes are not sensitive enough to look for cold neutron stars. So having said that, the smallest temperature that we've measured so far is 40,000 Kelvin. So a factor of 20 higher than the temperature I'm proposing here. And that's exactly why we are asking for future telescopes to look at these colder neutron stars, which are much more abundant in the galaxy.
Yeah, but during gravitational collapse very recently, during this multi-messenger thing, people have even observed the cooling curve of the neutron star, right? How a neutron star is cooling down, and
those cooling curves go down to a temperature of 40,000, or sorry, they go down to a temperature of 10 power 5 Kelvin and no more. So about up to about an age of 10 power 7 years. And all of this is an observational bias, because our telescopes and our technology only lets us look at these neutron stars. But in the future, this is definitely changing.
Thank you, Nirmal. It was a beautiful talk, but like Raj, I think our connections go bad. At least I got disconnected 3 times.
Oh, I see.
Yeah, and we have to reconnect. The IIT network has been unstable. Raj, you had the same issue, right?
Yeah, exactly. It got disconnected exactly 3 times.
Yeah.
Perfectly.
So can you contact the computer center and inform them, because I have been after them. So this has been happening too regularly.
I think the network has been pretty bad of late.
Yeah. Sorry.
You can watch it later though.
yeah.
So any more question to Nirmal? Okay, if not, Nirmal, could you respond to what I was asking you earlier?
Yes, definitely. Yes. So I remember the first question. Can you remind me of the second question a bit? later. So
the second one was about whether there are this new condensed matter devices, solid-state devices using
Indeed.
many body phenomena, whether you could detect dark matter better.
Indeed.
Yeah.
Okay, so for the first question, so when I joined IIT Madras, I was actually in the civil engineering department first, but I could not envision life without physics. So I actually worked hard in my first semester and got a branch change. And although I could have, in this IIT, there's a branch rankings, right, where the computer science is first and electrical engineering second and so on. I could have gone to those branches, but no, I wanted to do physics, and my way of doing it was engineering physics. So I came into engineering physics, and I was not disappointed at all. I didn't particularly appreciate the electrical engineering courses, but I loved all the physics courses. I took master's courses and so on. And in particular, my last 2 years, which is when I was exposed to Suresh and Rajesh here. That is when I learned that physics is not all about cool stuff, and it's not all ball bearings and springs. There's a lot more to it. You need to expand your intuition, and for that you need rigor. And they instilled the love of theory in me. In particular, when I took Suresh's course on classical field theory, that instilled a theoretical rigor in me, and then I carried that over to my project with Rajesh Narayan. And I really loved the project that I did with him. It was fascinating for me that the abstract equations that I was writing down there was actually a very logical connection to reality, and that was the power of field theory. And I did want to do condensed matter, although Rajesh may not agree with me. When I went to Oregon, I wanted to do condensed matter, and I was very taken by John Toner. And he was the one who suggested that if I loved field theory, that I should also try particle physics, and that's how I transitioned to particle physics. So yes, IIT Madras was where it all started for me.
Good. And
as for the sorry.
So Nirmal was an absolute pleasure to work with. I mean, I had the most fun working with him. I don't think we have ever had a meeting where, we left the meeting essentially laughing our guts out, right? All the time. So
exactly.
It used to be a lot of fun working with him. I'm sure it will be a lot of fun once he comes back too, if he decides to come back. I would really like it if Nirmal decides to come back. It will be great fun to have him here, I think. It's amazing to see how well he has done. It also makes me a bit proud that he has done so amazingly well.
Definitely.
Okay.
Okay.
That was good to hear. And
okay, so as for detector materials, so down here, maybe this, right. So down here, the region where condensed matter ideas, I think, would be most applicable would be in the low mass frontier, which is one of the hot frontiers of dark matter searches these days. And in particular, so there's already a lot of cryogenic readout technologies that are being used in experiments like CREST. There's a new one called SuperCute that's coming up, and Super CDMS and so on. But also people are talking about using, so you mentioned many body, so I want to talk about that. So using a couple of many body techniques, one being using superfluid helium to look for the lowest momentum transfers from dark matter coming from the lowest masses, as low as like an MeV or something. The idea being that the energy gap is so small that you would be able to trigger superfluid helium and see the phonon release in the material. Another idea, which I don't really understand, so I'm just going to say the words, is people are talking about Dirac materials, and they say that could also be used. The many body effect could also be there. It could also be used to look for low mass dark matter, lower than even an MeV. But I don't really know what that means, so I'm not going to comment on that.
Okay, Nirmal.
That
yeah, it was it was useful to hear that. Yeah, thanks for spending spending so much time to give us such a nice colloquium level talk, and it was quite nice actually. And so hope to see you do more great things in the future, and do visit us.
Definitely, of course. Yeah, next time I come home, it'll be great to see you in person also, Ayan.
Yeah. Great. Same here.
Bye, Nirmal. See you.
All right, Rajesh.
Bye.
Okay.
Bye. Thank you.
Bye, Raj. Bye,
Bye, Ayan.
Suresh.
Bye.
Nirmal.
Bye.
Okay,
See you, Suresh. Thank you. Bye bye.